electrodynamics. We have already done with our 2 lectures in which we have studied all about electric field, all about the force generated by the charges, all about the point charge, the types of symmetries, the types of charge densities, and Gauss law, obviously the applications of Gauss law, and all about related to the charge and electric field. So we have studied. Now, from this lecture, we are moving towards the advanced electrodynamics. In the last 2 lectures, what we have studied all was related to the BSc and MSc courses. Okay, related to the engineering courses also. And that all was some basics, some fundamental physics. But now the physics will get specific role and will get its specific form in which we will study in or this lecture number 3, divergence and curl of electrostatic fields, laws of electrostate, Laplace and Poisson's equations, uniqueness theorem, and boundary conditions. So, divergence and curl of electrostatic fields is an easy topic. So, we will not take much time, but the rest are some important topics from electrodynamics. So, today's class is quite important with the aspect of exams. So, please listen me carefully. I will Okay, listen me carefully. I will, with example, explain you all these equations, Laplace and Poisson equation, uniqueness theorem, and boundary condition. And these topics will help you to solve some problems of 5 marks in your exams. So, the divergence and curl of electrostatic fields, from this topic we will start, and we'll start with the format of charge. Here on your screen, you can see that there is a point charge situated in the center and the field lines are coming outside. So, do you guys know what type of charge it is? Is it a positive charge or it is a negative charge? Anyone can tell me, just watching this diagram, can you observe?
Is positive charge.
Yes, it is positive charge because the arrow of the field lines are towards out towards the charge. So the charge is obviously positive, and we are taking here one example of a point positive charge, and we know that electric field in a positive charge is this one. So let me have pen. Okay. So the electric field is this one from the Coulomb's law, we know that. So if we are considering this positive charge and these arrows are the denotation of field lines. Okay. And these also denote the direction of electric field. And from this diagram, we want to convey that number of lines per area means flux is proportional to E electric field, that you already know from the Gauss law. So basically the concept of divergence starts from here. You can see around a positive charge, if there are many field lines coming out of this charge and they have in various directions, so a type of symmetry can be formed. This type of symmetry we will see. Okay, we can assume that this symmetry can have this form also. So what is this form? This form is a bit of thread in oil which is aligned with the field lines. So what do you understand by this? We can understand that this is the origin or the center of these field lines, and n number of threads are coming out to this origin, and they are forming this type of structure. So this structure is quite similar to this one. So when we talk about the storms in ocean, then you have already know that all those storms have a center point from where they start, and at that center point the force is maximum. If someone is stuck in a storm, then the journey of the person will end to that center, because that center attracts all the things. The same is happening here. It is the center, and if it is a positive charge seen in this picture, so if the center is a positive charge, then electric field lines are coming out of this, and we can say that all the electric field lines have the same center. So this is the concept of divergence or curl, that all the laws or all the operators related to the electric field or force in electrostate have the specific center, or one center in which all the laws are aligned, or we have to follow that center in our problems by symmetricity. Okay, moving ahead, this is a schematic diagram of denoting two charges, and you guys can see that these two charges must have opposite sign. If we are considering this one as a positive charge and this one as a negative charge, then from the positive charge the electric field lines will come out, and to the negative charge they will get in. And for all the electric field lines, the process happening is the same. So when we are considering this type of diagram, we can assume that if it is happening on a line or on a thread, then we will consider some line charge density, and the electric field due to this structure will be E equals to this one. We can solve this equation and get the results. So what is happening here? The process we can see here by this. Okay, if two similar charges are there, positive and positive, then it will look like this. Two centers, we are taking example of ocean storm. So two center, okay, and all the field lines going outside of these centers. If the charges are opposite in sign, then two centers, but the field lines are starting from one origin and ending to another origin, starting from one center and ending to another center. So these are some exemplar denotation of divergence and curl. Okay, so the construction principle of field lines, you know that they start from positive Q and end at negative Q. The number of lines is proportional to the charge. If total charge is different from zero, there will be lines going to or coming from infinity. Field lines never cross. Field lines point in radial direction, and etc. etc. So these are some characteristics or construction principles of the electric field lines that you have already studied in your 11th or 12th standard. Okay, so we'll talk about the divergence of electric field, which is also a form of Gauss law. So you guys already know about the Gauss law. So Gauss law has two forms. It can be written in integral form, or it can be written in differential form. If we denote Gauss law in differential form, then we have to operate that electric field to its divergence. We have to calculate the divergence of electric field. So how can we do this? So a point charge, if S is the surface which is enclosing that charge, so we are getting closed integral S E dot d equals to q over epsilon naught. You know all the meanings of those terminologies. and the integral form must be closed integral E dot dA equals to Q enclosed over epsilon naught. Where what is that Q enclosed? Q enclosed is the total charge enclosed in that closed surface or in that symmetrical shape, which is equal to integral of V rho d tau. What is rho here? Rho is the volume density, and d tau, this d tau is the volume integral. In this integral, we will integrate the function in the form of volume operators or volume denoters. So this is the integral form. If we want to convert it into a differential form, then what we can do, we can just replace this q enclosed by this raw d2. So this raw d2 will come here, and this close integral as E dot dA, we will convert this from the Gauss divergence theorem, which says that the surface closed integral of any field is equal to its divergence integral with volume. So we can convert this, and from this equation we can get this differential form. So what we are getting? We are getting the divergence of electric field, which is equals to rho over epsilon naught. This thing will connect to our next topic, which is Laplace and Poisson's equation. We will get the similar equation. So just keep in mind what is the differential form of Gauss law, that is del dot E equals to rho over epsilon naught. Okay, now we'll talk about curl of electric field. So for the point charge, for any point charge, the electric field E equals to kq over r square in the direction of r cap. Okay, so we have a point charge q, and when we want to derive the curl of this electric field, what we are getting? We are getting the value 0. Del cross E equals to 0. The condition also is there. If del cross E equals to 0, then close integral E dot A will always be 0. Why? This is coming from the Stokes theorem of curl. Stokes curl theorem. So in Stokes curl theorem, how we can convert? We can convert a line integral into a surface integral doing the curl of that vector quantity. So we are getting this thing. So, okay, this is remaining true if electric field E is equal to summation over I EI. That means the total electric field is the sum of all the smaller electric fields generated by different places by a point charge. Okay, so this condition is only true if we are following this rule. Okay. So these are some general properties. Now let's talk about some laws of electrostates. So these two things we have studied about. Okay, del cross E equals to 0 we know, and that is why close integral E dot dA is also equals to 0. And this is a differential form of Gauss law. So this rule will also be included in the laws of electrostatics, and this is the integral form of Gauss law. So basically, these are the laws of electrostatics. These four are the laws of electrostatics. Always keep in your mind, uh, one question can come from here, that there must be four options, and one can ask which is not the law of electrostatics. So only these four are considered as the standard laws of electrostatics. There are many laws of electrostatics. We will use many equations in electrostate, but these four are always true for the point charge. Okay, for the symmetrical surfaces, and for using Gauss law, and for using Coulomb's law. So these are the laws of electrostatics. Okay. Moving ahead, now we'll discuss about Laplace and Poisson's equations and uniqueness theorem. Let us have some brief idea about these. So first of all, what is a Laplace equation? You must have heard about Laplacian operator in your mathematical physics. So Laplacian operator is basically the double derivative of any vector quantities. It is basically del square, double derivative. Okay, and Laplace and Poisson equation are the extracts of Gauss law in the differential form. And uniqueness theorem is the word is coming uniqueness now. So what it is telling? It is telling us that it must be related to some unique thing. So uniqueness theorem is telling us that any solution of any problem in the electrostate have its uniqueness, means a problem in electrostate always have a unique solution. There may be different ways of solving any problem, but the answer is always one, and that answer is unique. Okay, we'll discuss briefly. So in realistic electrostatic problems, one seldom knows the charge distribution. Thus, all the solution methods introduced up to this point have a limited use. Okay, limited use. Second one is these solution methods will not require the knowledge of distribution of charges. So we will use two solution methods now. Laplace and Poisson's equations we will use. So keep in always mind that we can't get any idea about distribution of charges. How? We'll solve some problems and then you will get to know that why I'm saying this. Okay, so basically Laplace and Poisson's equations are on your screen. We are deriving just two equations. We are starting with the Gauss law in point form. So you guys know the differential form of Gauss law, which is del dot D equals to rho v. We have already discussed in our first lecture. This was a form of Gauss law. Del dot D equals to rho v. D is the displacement vector, and D can be also written as epsilon E, where E is the electric field. Okay, why this E bar here? Because we are talking about the average field. Okay, so epsilon E bar. What is this epsilon? Epsilon is the relative permittivity of that medium. Okay, so we are using that gradient concept of electric field. This equation also we have discussed in our lecture number 1. So E was equal to minus del dot V, and what we have to do, we will just put the value of this E on this one. Okay, this E can be replaced by this minus del V. So we are doing this, and what we are getting, this minus sign will come here, and del dot del V equal to minus rho V over E we are getting in equation 3, and thus we are getting del 2V. What is this del 2? This is del dot del, which is del 2 or del square, which is an operator which is called a Laplacian operator. This del square is Laplacian operator, and thus we are getting this equation number 5, which is del 2V equals to minus rho V over epsilon V volt per meter square. It is V per m square, and this equation is Poisson's equation. Okay, this equation is Poisson's equation, but this del square is Laplacian operator. Okay, so it is called Poisson equations, and the Poisson's equations we always apply to a homogeneous media. And what is homogeneous media, we will discuss in our next lecture. Okay, so if we have no charge, so we will not get any charge density. So if any case comes where there is free charge density, that means rho v is equal to 0. So if rho v is equal to 0, then what we will get? Put this put a 0 instead of this rho v, and you will get this term as 0. So we are getting del 2 equals to 0. Now it is the Laplace equation. Okay. So a minor difference between the two equations, Poisson equation and Laplace equation. What is Poisson's equation? Poisson's equation is del 2 equals to minus rho over epsilon, and Laplace equation is for for the fields having free charge density. That means rho v equals to 0. So del 2 v equals to 0. What is this del 2v? This del 2v is a rectangular coordinate, means the Cartesian coordinate. So in rectangular coordinate, del 2v equals to del 2v over del x square plus del 2v over del y square plus del 2v over del z square. So these two equations are easy and even they are easy to use. Now, what is the uniqueness theorem? I have told you guys already that uniqueness theorem is all about stating a unique solution for any problem in electrostate. So, the uniqueness theorem states that for a V solution of a particular electrostatic problem to be unique, it must satisfy two criteria. We know that the solution should be unique. So what criteria it should follow? So the two criterias it should follow. The first one is it should follow the Laplace equation, and the second one is it should follow the equal potential on the boundaries. So here we will also apply our boundary conditions, and what are those boundary conditions you will get to know within few minutes. Okay, so first of all we will do one example to understand this uniqueness theorem. So what is this example saying? In a problem containing two infinite and parallel conductors, one conductor in Z equals to 0 plane at V equals to 0 volt, and the other in Z equals to D plane at V equals to V0 volt. We'll see later that V field solution between conductors is V equals to V0Z over D volt. So this solution will satisfy Laplace equation and the known boundary potentials at Z equal to 0 and Z equals to D. Just try to understand this problem. The problem is that one conductor is in Z equal to 0 plane at V equal to 0 volt. So this is a conductor. This is over Z. Okay, this is over Z, and it is situated at Z equal to 0 plane. Okay, this is Z equal to 0. This line is Z equal to 0. Okay, now on that Z equal to 0, it has voltage V, which is also equal to 0. Okay, V is also equal to 0. Now there is another plane. Another plane is there, like parallel to this one, which is at some distance d over z. So now this plane is upon z equal to d. Okay, so at z equal to d plane, v is equal to v0 volt. Now this potential v is equal to v0. Okay, this is the situation, this is the problem. Now we have to solve we have to calculate the field solutions between these two conductors. So how we can get the field solution, we'll see later, but let me tell you, we will get two field solutions because there are two different potentials and both the conductors are situated on two different distances at the z-axis. So for this z equal to 0 plane, V field solution have V equals to V0Z over D. One solution will be like this, V equals to V0Z over D. And for this Z equal to D conductor, this plane at where V is equal to V0, we will get V field solution like this. So we are getting two solutions. Okay, now we have to calculate the unique solution to satisfy our uniqueness theorem. So what we will check? We will first check whether this V satisfying the Laplace equation or not. So this v equals to v0 z plus 1 over d is satisfying the Laplace equation. Okay. Now, this v equals to v0 z over d is also satisfying the Laplace equation. Next, what we will check? We will check the potential on the boundaries. So this first one will not give the boundary potentials. I will tell you why. And this second one will give the will satisfy all the boundary conditions. So will give the boundary potential. So the unique solution of this type of problem will be this one. So this one will be the solution. Okay na? So this is the simplest example of the uniqueness theorem, how we can choose the unique solution for any problem. So let us do some questions or examples to see whether we can solve any problem using uniqueness theorem or not. So this is example number 1. Two infinite and parallel conducting planes are separated d meter with one of the conductor in z equal to 0 plane at v equal to 0 volt and the other in z equal to d plane at v equal to v0 volt. Assume rho v equal to 0 and epsilon equals to 2 epsilon naught between the conductors. So the this problem is similar to the first one. We have seen the example, so the diagram will be same, just one difference. The difference is this one: epsilon is now equal to 2 epsilon naught between these conductors. What we have to calculate in this example, we have to calculate volt in the range, means potential in the range z is less than 0 and greater than 0 and less than d, electric field between conductors, and is d between conductors, dn on the conductors, rho s on the conductors, and capacitance per square meter. So we have to calculate all these things. Any one of this quantity can be asked in your exam. These are some specific examples I have extracted in this lecture for you guys, that you should, so that you can have some practice to solving these types of problems. These are some problems which are coming in the exams frequently. So we have to solve these types of problems more and more. So this is the solution. First of all, rho v equals to 0 is given in the question. So it is a charge-free region. Okay. If it is a charge-free region, then we will direct apply the Laplace equation. We can't apply here the Poisson's equation because there is no rho. So the Laplace equation in Cartesian coordinate is this one: del 2v equals to 0. Now, if we are talking about only z plane, look at this problem. We are talking about only z plane. This z equal to 0 plane, this z equal to d plane. So the potential will also have only z as a function. There will no be the two axes x and y. So those x and y are already 0. So del 2v is equal to del 2v over del z square, which is equal to 0. So if del 2v over del z square equal to 0, so we can write this as this one. We can write this now. So del 2v dz over dz, and here also a dz equal to 0. First, we will integrate this. So the integration of 0 is a constant. We are putting a constant a. So we are getting dv over dz equal to a. Again, we will integrate this. So we are getting v equal to az plus b. Now, we have considered that it is already satisfying the Laplace equation, and we have the solution of potential. Now we want to know the values of this a and b. So what we will do, the second thing we can do for a unique solution, we have to apply boundary conditions. So now we will apply boundary conditions. So the first boundary condition will be at z equal to 0, and the second boundary condition will be at z equal to d. Means both the conditions are given in your question also. So a and b are constants, and we will evaluate these. So v at z equal to 0. So if I put this 0 instead of this z, then I am getting v equals to b. So v equals to b equals to 0. And if we are putting this z equal to d, then we are getting, if this z is equal to d, and we already know that b is 0 now. So b is 0. So we are getting v equals to ad. So let us assume this ad is equal to v naught. So we are getting a as v naught by d. Now we know one constant. What is that? A,
Uh,
which is, yes.
Monica, this is Ankita. I think your voice is breaking. Or anyone else feeling the same, or it's the issue at my end?
No, ma'am.
No, ma'am.
I don't have any issue.
Oh, so okay, so continue, ma'am. No problem.
Okay. Okay, so we have now calculated one constant, which is A. So what we will do, just put the value of A here. Okay, so we will move to the next slide. Okay, so this is our A. So we are getting V equals to V naught Z by D. We also know that B is 0 and A is V naught over D. So this is one solution for V, which is in this boundary condition, Z is greater than 0 and less than D. So we can calculate the potential. And what we have used only two things. We have satisfied the Laplace equation, and then we have applied the boundary conditions. So it is quite easy. Next, if we want to calculate the electric field, then we know that E is equals to minus del V. Just do that. We can get the electric field also. And if we want to know this displacement vector D, then we know that D is equals to epsilon E, and this epsilon is given in the question. That was epsilon equals to 2 epsilon naught in between those two conductors. So just put that value to epsilon naught, and we can derive this D also. The next is we have to derive that surface charge density, that is rho s. So we will calculate this rho s on the both plates. The first plate was at z equal to 0 and the second plate was at z equal to d. So this charge density will be calculated on both. So firstly we will calculate for z equals to 0. So always keep this formula in mind. This is a new formula. We will not discuss anywhere. So just note it down. That is rho equals to d dot n cap. N cap is the conventional direction and d you know already. So just put the value of that d, and we are considering the direction z now. So just put that z cap, and this z cap and z cap will make a unit vector, which is 1. So we are getting this. And at z equal to d, so at, if we are considering z equal to 0 as our origin or as the starting point, then the z equal to d we will also consider, we will always consider in the opposite direction. If it is z equal to minus d, suppose the question is like we have to solve this for minus d to 0, then for z equal to minus d it will also be minus z cap. So the direction for the second boundary condition will always be opposite to the first one. So the conventional direction will be minus z cap here, and we are getting this one. You can also remember, like the first solution will be in minus and the second will be in plus. So you can also remember like this also. Next, we have to calculate capacitance, and we know that the capacitance is charge per voltage, charge per volts, charge per potential. So this charge is rho into ds. So we know the value of rho. Just put that, and we can get this solution. So this is the way to calculate all these things. Some more examples are here. The first example was for Cartesian coordinates, and the second one is for cylindrical coordinates. And this example says two infinite length concentric and conducting cylinders of radii A and B are located on the z axis if the region between cylinders are charged P and epsilon equals to 3 epsilon naught, V equals to V naught volt at A, V equals to 0 volt at B, and B is greater than A. Then find the capacitance per meter length. So the question is saying that we have cylinder. So if we have cylinder, then we will use the cylindrical coordinates, and the del 2v in cylindrical coordinates is this one. You have already been studied in your mathematical physics. So you know this thing. So the process is same. Just satisfy the Laplace equation. Just solve that Laplace equation. You will get two constants A and B. Then put your boundary conditions at r equal to a and r equal to b, which is given in your question. Just calculate those two constants a and b and put in your solution for voltage, and then you have to calculate the electric field, then you will calculate the displacement vector, then you will calculate the charge density, and at last, from using the values of charge density, you can calculate the capacitance. So we have to calculate the capacitance per unit length. So per unit length means capacitance per meter, capacitance per length. So that is why this is DL here. We are talking about the length. Okay, so these were two types of solutions, and the next one example is two infinite conductors form a wedge located at. What is a wedge? A wedge is a wedge shape is like two planes inclined over one to another at some angle theta or phi. That shape is called a wedge. So two infinite conductors form a wedge located at phi equals to 0 and phi equals to pi by 6 as shown in figure below. If this region is characterized by charge free, means rho equals to 0. Find V and E bar. Assume V equals to 0 volt at phi equals to 0 and V equals to 100 volt at phi equals to pi by 6. So some numeric values are given, and now you can solve this example because now you know the recipe to solve these types of questions. So you have given the boundary conditions, you have to calculate the potential and electric field. So the same recipe, these are cylindrical coordinates, so we have to follow that del 2v, and we will get two constants v in the form of two constants a and b. We will put the boundary conditions, we will get the potential. Some numeric values were given in this question now, so we will get some numeric values in answers too, and thus we can also derive this electric field, which will be minus 600 over pi r phi cap. Another example, which is in spherical coordinate, we have calculated in Cartesian coordinate, we have calculated in cylindrical coordinate. The next one is in spherical coordinate. So some numerical values are also given. So these examples you guys can now solve. So I think you will always remember the recipe to solve these types of problems. You will use Laplacian operator with that potential vector, and del 2 equals to 0. If given in the question that charge free region or rho equal to 0, then you will use that Laplace equation accordingly. If Cartesian coordinate, then apply that Cartesian coordinate operator. If cylindrical coordinate, then rho, phi, and z you will use. If spherical coordinate, then r, theta, and phi you will use. And you will get some values of potential in the form of two constants a and b. Then you will apply the boundary conditions. Then you will solve them for electric field also. So now you have learned these things. This is one more example here. This example is not the same to the previous examples because here rho v is not equals to 0. So look here, if there is given in the question that charge density is not zero. That means it is not a charge free region. What will you do? So this is example number 5, which states that two infinite and parallel conducting planes are separated d meter with one of the conductor in x equal to 0 plane at v equal to 0 volt and the other in x equal to d plane at v equal to v0 volt. Assume rho v not equal to 0 and epsilon equals to 4 epsilon naught between the conductors. We have to find V in the range x is greater than 0, less than d, and electric field E between the conductors. So if charge density is not equal to 0, we will not use the Laplace equation. We will here follow the Poisson equation. So what is that Poisson's equation? That is del 2V equals to minus rho V over epsilon. So this del 2V equal to minus rho V over epsilon and this x equal to 0 is given. So you can conclude that we are talking about Cartesian coordinate. So use that Cartesian coordinate and we are not any value of y and z here. So we will solve only for x. So del 2V over del x square will be minus rho naught over epsilon. And you will do the same. Just do one time integral, you will get this value. Two time integral, you will get this value. But here you are getting three different terms. You are getting a and b as two constants with some value having charge density, which is minus rho naught x square over 2 epsilon. Okay, we will consider this value in our next equation too. Next, we have to apply the boundary conditions. So b will be 0 from x equal to 0 and at x equals to d, we can solve this for a. We'll put the values of a and b from these equations. This b equal to 0 we will put and this value of a we will put, and in this region we will get this type of solution. So this is the only difference between charge free region and if the value of rho is given. Whatever the value, we will have one extra term for that row and the recipe is the same, and thus we can also calculate the electric field by just a single derivative with respect to that coordinate which is given in your question. This is a repetition of that example number 5. If rho v should 0 there, if rho v is 0 there, and we have given that epsilon r having the value 1 plus x or 1 plus chi, so we will solve by this method. So del dot d is used to be equal to rho v. We have given that rho v equal to 0. We will not use any Laplace equation. We will not use any Poisson equation here because we have not given the value of this epsilon. Instead of this, we have given a relation which is epsilon r equals to 1 plus chi or 1 plus x. So we will use this method. Okay, so this is the differential form of Gauss law. You know that, and you can solve this problem in Cartesian coordinate because in question we are talking about x. So again we will get two constants a and b and use the boundary conditions, and in that region we can get the value of v, which is again different from the previous value we have calculated. And from these examples you can also conclude that every problem has a unique solution, and thus we can get some electric field also. So this is the recipe, and using these types of examples, we will solve some problems from the CSIR NET paper. So now you know how to solve these types of problems. So here is question number 1. If the electrostatic potential Vr theta phi is a charge-free region has the form Vr theta phi equals to Fr cos theta, then the functional form of Fr. So we have to calculate the functional form of Fr, which means we have to calculate the form of potential solving the Laplace equation. And we will not solve, we will not use any boundary condition here because no boundary condition is given in the question. There are 4 options and the question is from December 2013. So we have given the potential, which is VR theta phi equals to FR cos theta. We know the Laplace equation, and this R theta phi means this is in spherical coordinate. So we will use that Laplacian operator in the spherical coordinate, which is this one. So please remember all these values of this Laplacian operator in Cartesian coordinate, in spherical coordinate, and in cylindrical coordinate, so that you can directly apply those function and you can solve those questions. So this is del 2v for spherical coordinates, and just put the value of v, which is fr cos theta. So we are putting this value of fr cos theta. If we are doing this del over del r of fr cos theta, then we are getting f dash r cos theta. And you can solve this mathematically. I am not going to tell you how to differentiate or integrate. So you can solve this thing, and thus you will get this type of solution: r square f double dash r plus 2r f dash r minus 2fr equals to 0. Now you have 4 options on your screen for this question. So we know that the solution must have this type of form. So we will put each option one by one. This is obviously a hit and try method, and the correct value of FR you can get, which will be option number B, which is equals to AR plus B over R square. There is another method to solve this problem. I have not mentioned here because that will not follow the recipe we were talking about in this lecture. So I will upload that second type of solution on the WhatsApp group by tonight, so that you can solve by that method also. But this method is appropriate to solve these types of problems. Okay, so you have to follow this method also. So question number 2 is, if the electrostatic potential in spherical polar coordinate is phi r equal to phi naught exponential minus r over r naught, where phi naught and r naught are constants, then the charge density at a distance r equal to r0 will be. This question is from NET June 2014. So we have to calculate the charge density. We have given the potential. We have given that we have to use the spherical polar coordinates. So this question is quite easy. Just use the Poisson equation. Use that del 2 in the spherical coordinate. Okay. We have given that the phi is only the function of r. Look at this question. Phi is only the function of r. So we will not use the second and third term of that Laplacian operator in spherical coordinate, means theta and phi are already discarded. So just I am putting here the only one term, that is del 2 phi equals to 1 over r square del over del r square del phi over del r. Just put the value of phi which is given in the question, which is phi naught exponential minus r over r naught, and you can solve this mathematically. This is simple to solve, and you can get this type of value at last. Okay, so you are getting del 2 phi equals to minus phi naught over r naught minus 1 over r naught exponential minus r over r naught plus 2 over r exponential minus r over r naught. We have to calculate the value of charge density at r equals to r naught now. So we will put this condition also. So at a distance r equals to r naught. So what they are saying, just to put r equals to r naught. So we will put r naught here and R naught here also. So this minus R naught over R naught will be exponential minus 1. This will be again exponential minus 1. So these are the terms. You can solve these and thus you can get the proper value of your charge density, which is phi naught epsilon naught over R naught square E. So the correct option will be option number A. Now these questions are looking quite easy because we know the recipe to solve these types of questions. Otherwise, these questions are quite hard to solve in the exams. The question number 3 is for a scalar function phi satisfying the Laplace equation del phi has, and there are four options: zero curl, non-zero divergence, non-zero curl, zero divergence, zero curl, zero divergence, and non-zero curl and non-zero divergence. So this question is from GET 2013 paper and the right option is C. Why? Because C, the question is del phi will satisfy amongst these options what it will satisfy. So this del phi, you know, if it will follow the Laplace equation, then del 2 phi should be equal to 0 na. So to get del 2 phi equal to 0, what we have to do, we will apply divergence. So it will have a zero divergence. So there are, this is in option 1, it is in option 2 and 3 only. So zero divergence it will always possess. The second thing is, if del phi is equal to 0, then we can also do the curl. If you will solve this one na, then also you will get the value 0. So this also will have a zero curl. That is why this option number C is the correct one. Next and the last question of today's lecture is the electrostatic potential due to a charge distribution is given by VR equals to A exponential minus lambda r over R, where A and lambda are constant. The total charge enclosed within a sphere of radius 1 over lambda with its origin at R equals to 0 is given by, and there are four options. In the last lecture, someone has asked me that, Madam, can we calculate the charge density using the electric field or potential? So I told her that yes, we can do. So look at this question. We have given the potential and we have to calculate the charge. And if we can calculate the charge, then we can also calculate the charge density. And if instead of this potential, the question will be say the like electric field, they give electric field in your question, then also you can solve for the charge density and the total charge enclosed. So we will use Laplace and Poisson equations for the charge density. So if you know that Gauss law is Q over epsilon naught equals to close integral E dot dA, na? So Q will be equal to epsilon naught close integral E dot dA. So just put the value of E and solve. This dA is will be in the spherical polar coordinate, which is r square sine theta d theta d phi. You will write, and when you will solve this, you will get this one. So this is 4 pi epsilon naught A exponential minus lambda r 1 plus lambda r. Equals to 1 by lambda. So just put the value of r. You can replace this r by 1 by lambda and this r also. So we are getting the solution 8 pi epsilon naught A by E. So now if you know the charge enclosed, then you can also calculate the charge density, which is rho. What is that rho? Rho is charge per unit volume. So this charge, you know, the value of volume you can calculate, so you can also calculate the charge density. Okay, and this question is for you guys. The solution is also given. Electric field is given, and you have to calculate the total charge enclosed. We have done one question like this. This question you will do. This is the solution. You can see and can solve this question. Actually, this is from just 2017, and there must be any option which is like same. We can get two options, so there was some discrepancy with this question in 2017, but while you will use this recipe now, you will get the correct answer. So all for today. If any query, then you can ask. Yes, any query?
No, ma'am.
Okay, so today's class was important, and please watch this lecture again. And if you guys get any query, then post it on WhatsApp group. Okay, sir.